Okay, I think this is working. Let me check. I'll just trust that the audio didn't work capture. Okay, here's today's problem. The smallest subtree with all the deepest nodes. Given the root of a binary tree, the depth of each node is the shortest distance to the root. Return the smallest subtree which contains all the deepest nodes. A node is called the deepest errors, the deepest depth possible among any node in an entire tree. The subtree of a node is a tree consisting of that node plus all descendants of that node. Okay. So, um, here's the input example, and they've highlighted the result. So, because 7 and 4, like, if we call depth, root is 0, this is like level 1, level 2, level 3. 7 and 4 are both level 3. So we need a subtree that encapsulates all the level tree nodes. Um, so 2 is our answer because it encapsulates 7 and 4. This is okay. So if there's just one node in the tree, which would be like this, that's the smallest node. Okay, so I guess that answers my question, which is like, if we pretended like this 7 wasn't even, would our answer just be 4? Um, because the subtree is just that node. Um, like there's only one node in level 3. I guess another interesting scenario is let's pretend like sorry, this is a little bit janky, but if there was just like a 3 and a 5, it's not a binary search tree. If the tree is perfectly balanced, then it would have to be the root always. I guess even if it's not perfectly balanced, like this one, well, I guess this is perfectly balanced. It's not full, but it's not. Yeah, so perfectly balanced is the root. Interesting. Okay. Um, can I get this example? Can I understand this example? Move this up to here. So I'm going to scroll down a little bit. So in this example, the root is 0. Apologies for the terrible handwriting. 1, 3. 3 doesn't have a. Oh, this is the example that I was talking about. This is the leaf nodes are just the answer. Well, it's not just leaf nodes. Obviously, these are leaf nodes, but okay. So I think I understand the problem. There are these like different like single node at deepest equals just that node, single node. I guess that's like this is stating the same thing, but just one node in a tree. That's the same thing. It's just the root and balanced tree, which I don't think we can really use because there's no assumption. It's, um. Okay, so now I feel like I understand the problem, so I'm going to go to brainstorming. So I can find the root, or I can find the level of a given node pretty easily. Recursion, it's like uh, level equals width level plus 1, and this previous level is like pass in, and like the first case you pass 0. Um, or you could pass -1, I guess, because it's like we want this to be 0. Or it could be 1. It doesn't matter. Uh, should probably pick one, so I'm going to say root level equals 0. Um, so for any given node, I can find the um, the depth of the node, and it also makes me think that we probably visit all the nodes at least once, because what if there is a deeper node somewhere? Another example that's like maybe interesting to think about is like a little unusual. I guess not that unusual, but like if we had a root here, it's like even though these are going off in different directions, it's like, you know, the the answer is this two here, the root. Um, okay, so right, and I just say that because like if you don't visit all the nodes, like how do you know that then there isn't like a 7 over here, like another node over here, then your answer would be this node right here, as opposed to the root, like that totally changes your answer. So I think that makes me think that like the like minimum time complexity is going to be O of n, where n equals number of nodes. I'm not saying that's our time complexity. I'm just saying like we'll need to visit all the nodes at least once. Then what do we do? So once we have, um, I mean, we could find like what's the like we could traverse the tree one time, find level of deepest nodes. There can be ties. Like these two nodes are deep, they're at the same level, that's a tie. And then so we have like max level equals, in this case, it would be 0, 1, 2, 3, 3. Then what do we do with that? So I guess it's like uh, find a node where all the nodes below it are that level, something like that. Um, so like if you look at this 3 here, root level set equals um, I guess like 2 and 3. This one right here, this 5, 5, it's like level set equals um, 2, 3. Same with this. Well, this one's level set here is just 2. And this is like its descendants, like 2. This 6 level set is just like just itself level set equals 2. This 4's level set equals, or excuse me, this 2's level set equals um 0, 1, 2, 3, 7. I'm still not sure this is what I need to do. Okay, so maybe there's an answer here. I don't see like the logic quite yet. Let me take a look at this other example. Would be a more interesting example. Is this an interesting example? I guess so. Okay, so it's like, I guess the level set has to include itself, and it should include all of it. Maybe, right? That seems like maybe a waste. It's like the level set of is it like, am I tracking, I'd be tracking level set of the leaf nodes of its leaf nodes, or all nodes. Seems like maybe the leaf nodes. So like if I yeah. So this roots level like leaf level set is 2 and 3. Five's level set is 2 and 3. One's level set is just 2, but that's not the that's not our answer. So they can't be that. Um Six's level set is just itself 2. Two's level set is its set all its leaf the set of all the nodes maximum depth is 3. That's our answer. Seven's also 7 4 also 3, but because there's like an answer above it, that's like the correct answer. Um, yeah. Okay, I'm not quite there, but I think I'm getting closer. So going to this example, the like 1 0 1 2. Whoops. So root leaf level set equals. It says 3, which has a level set of 1, and this 2, which has a level set of 2. 1 that has a leaf level set. Oh, it's not just leaves, right? Because this 1 isn't the right answer, right? No. Hmm. Yeah. What am I missing here? There's like just a way to think about this that I am not quite getting. Um, green level set. Like I think I'm close, but I'm not quite there. Because like my reasoning kind of works, even though it's not fully spelled out for this case, but it doesn't work in this case. Like the same reasoning. Um, I need to reread the problem again, just to see like if there's a word that stands out. Given the root of the binary tree, the depth of each node is the shortest distance to the root. Turn the smallest subtree such that it can all the deepest nodes in the original tree. Um, yeah. So I guess I could also like count deepest nodes. Um, count deepest nodes. Question mark. So like in the first example, you have 2 deepest nodes, and you know that because you know the max depth, and we count. We could retrace down to the leaves and count their depth and say, like uh, reference. Anyway, you could do it. I won't worry about pseudocode right now. In this one, we know we have 1, so it's like, oh, interesting. Okay, so is it just you have 2, so you go up 2? No, that can't be right. That can't be right. Because if there was 3, wait, 1, 2, 3. Maybe that is right. Okay, well here we have all right. That's so tiny. That's not what I want. Deepest nodes equals this node count equals 2. Um, yeah, and we can go up 2 from the deepest nodes. Does that work? Is that like a general thing? So the deepest node count is 2. You don't go up 2. No, that doesn't work because we have 2. Yeah. No. Okay. Scratch that. But I think it does. I think knowing the deepest node count is really helpful. Um, so like 0, 1, 1, 0, because maybe you could label the nodes by their deepest node count. I want to mess with this example. I'll try to do a better job. I'll even type it out and zoom in. So 3, 6, 2, 0, 8. Uh, and okay, I feel like I'm being really slow, but that's okay. And I'll just try to make this a little bit. Okay, so let's say like we're defining a new value, which is like this subtree. How many of the deepest nodes does it have? So for 7, its subtree, which just itself has one of the deepest nodes. Same with this 4. This 2, it has 2 of the deepest nodes. For this 6, it has 0. For this 5, it has 2. For this 3, it has 2. For this 0 has 0. 8, 0, 1, 0. So you then find like the deepest node with this value. Um, I think that's pretty decent. Let me go back. So for this one, it's 1, and there is only 1. It's 1, 1, 0. Okay. This is 1, 1, 2, 1, 1. And we have to look for 2. Okay. So I think that's the vibe. You're looking for also the deepest subtree with all of the deepest notes, right? Um, so find the deepest notes. Okay. The number of okay, we've already talked about this. So I think this might be really inefficient. There might be ways to do this, but it's like 1, count the find the level of the deepest notes. 2. Um, I mean, you could like think be like a depth first search of the sub tree with the deepest nodes count. That equals. Do we need to like? Um, this might be. I might be able to do this in 1, 2, and 3 in one step. I'm not sure yet. I'm going to come back to an optimization later, possibly combining these two. I'm not sure I can do it, but it seems like probably might be able to. Um, okay. Then like the first time you find it, that's your answer, and you return to the tree. Um, so I'm gonna do. Oh right. So I guess like one is um like recursion node level. Um, if like node, right? I guess like depth left equals node dot like recursion dot left level plus one depth right equals recursion of node dot right level plus one, and then returning maps of the two depths. There's also base case. It's like node filtering. You're a leaf, and so you just return your level. Okay. So let me just see. So, and the starting case root 0. So 0, I'll go 0, level equals 1 here, level equals 2 here. Left is 2, level equals 2 here, level equals 3 here, level equals 3 here. Left and right depth. Max is 3. 2 and 3, max is 3. So this side is 3. Okay, I think this works. So here, another recurring. Node level. Base case. No children. Back to see if level equals mass. I guess there's also this mass equals. Um, with yes, become 1. Okay, so that's base case like no children. Um, and it's like left equals recursion dot left level plus 1. I guess it's a pretty Pythonic pseudocode. That's okay. For a friendly recursion. So let's see. Oh, I guess yes. Because if count right, well, I guess like you could return a couple things. You could return like you could return this count. To combine the two, you could maybe return the count and like the count returns node or deepest node count and in insert. So this would be like one answer is this. Yeah. Yeah. Uh, yeah. This actually doesn't matter right here. Because we just need the node. Yeah. So once we find the answer, it doesn't actually matter to you track it and answer. Like we haven't found it yet. Okay. think I'm ready to move on to step three. Code it up. Well, okay. Just real quickly. Yeah, I think I'm ready. Okay. Divas. There'll always be a root. So okay. Wow, I didn't even notice this constraint. The values of the nodes in the tree are unique. I'm not sure that matters here. I don't think the values in the nodes of the tree matter at all. I'm not going to access them at all. Okay, so if and if node left node right is non neutral, return null. Okay, so now um, I'll say um, that left equals 0 if left is not known, except depth equals um, or recursion. And this is an okay default because there's always at least one node. Okay. Okay. And insert the count and a optional so if now and then okay. So we don't have the answer, but we need to check if we are the answer. So what did I call it? This is okay. I missed this. Check if we are the answer. Whoops. I knew my pseudocode was not to stop. Okay. Okay. Let's take a look at our cool example, or like a little bit cleaner example. Make sure it works. Yeah. Oops. Okay. So, oh, I forgot to do time complexity. Well, I started talking about it. The runtime complexity is O of n. Space complexity also O of n, I believe, because recursion, because of stack rooms. I actually don't totally understand. I should double check. I think that's right. Okay. Um, so, okay. So, first deepest level. This is false. Zero. So this is false one. False two. Two. Okay, so this should be. Oh, I haven't done my. I don't know why this accepts an optional tree node. Okay, so the global is 3. Okay, so in this case, so this level is 2. That's not equal to 3. So this. Okay, so this is returning 0 here. Then we go down here. This is returning 1. But because 1 is not equal to 2. Wait, shit. I I still need the count. I can't combine. Do I? Do I still need the count? Maybe I could do combine 1 and 2 here. No, because I. Oh my god, that was a real mess. Okay. Whew, what a mess. Okay, but we got through it.